Hey there, and welcome to this explainer. I want you to imagine, just for a second, stepping onto a raw construction site. It's rugged, it's uneven, and honestly, to the untrained eye, it looks completely chaotic. But before a single brick is laid or a single road is paved, that chaotic terrain has to be translated into absolute mathematical certainty. That amazing transformation is the art and science of surveying, and specifically, we're talking about leveling. Today, we're going to explore exactly how engineers manage to turn a jagged, unpredictable landscape into a perfectly engineered reality. Let's get into it. All right, here's a quick look at our roadmap. First up, we'll cover the foundations of leveling. Second, the surveying instruments themselves. Third, we'll look at field methods. Fourth, we'll dive into calculating the reduced level. And finally, number 5, eliminating errors. Section 1, Foundations of Leveling, the why and what. So, why does achieving true flat even matter in the first place? Well, whether you're trying to ensure the structural integrity of some massive bridge or you just need to guarantee that water is actually going to flow smoothly down a meticulously graded canal, understanding elevation is literally the bedrock of civil engineering. At its core, leveling is simply the operation used to determine or compare the relative heights of points on the Earth's surface. We're essentially establishing a horizontal line of sight to see exactly how high or how low one point is compared to another. To do this, we need a shared vocabulary. First, a level surface is a curved surface that's parallel to the Earth's shape, while a horizontal line is a straight, flat line that's tangential to that curve. But the absolutely crucial term you need to know here is the datum. A datum is our baseline. It's an arbitrary horizontal surface from which all other elevations are measured. And what's really wild is that in most topographical work, this datum is mean sea level, which is actually calculated by averaging high and low tides over a period of about 19 years. Pretty incredible, right? Moving on to Section 2, Surveying Instruments, the tools of the trade. Okay, so we've got the theory down. Now, how do we actually bring this to a physical job site? Well, the surveyor's toolkit has evolved a ton depending on the classification of the survey. For your standard jobs, we traditionally use a manual dumpy level or an auto level, which has this neat self-compensating pendulum. But for high-order, super precise leveling, where literally every millimeter counts, we use digital levels. These read bar-coded staffs electronically to completely eliminate human error. And alongside the level itself, you absolutely need a tripod for stability and a leveling staff, which is basically a graduated rod held vertically at your measurement points. Taking a closer look at the anatomy of the classic dumpy level, you'll notice that the telescope and the vertical spindle are actually cast as a single, solid unit. This means the telescope is totally restricted from moving up or down. It only rotates horizontally. It sits on a leveling head equipped with foot screws. The surveyor uses these screws to perfectly center that little spirit bubble attached to the telescope. Once that bubble is dead center, boom, your line of collimation, your line of sight is perfectly horizontal. Now, you can't just drop the tripod down and start taking readings. At every single station, the surveyor has to perform what are known as temporary adjustments. They're called temporary because, well, they have to be repeated every single time the instrument is moved. First, you set up the tripod firmly. Second, you do some approximate leveling with the tripod legs. Third, perfect leveling using those foot screws until the bubble is perfectly centered. Fourth, you hold a piece of white paper in front of the glass to focus the eyepiece until the crosshairs are razor sharp. And finally, focusing the object glass on the staff to eliminate any parallax. It's quite the ritual. Section 3, Field Methods, Adapting to the Terrain. So now our instrument is perfectly tuned. How do we execute the measurements? Because as we know, terrain is rarely cooperative. If 2 points are close and visible, we just use simple leveling. One setup, right in the middle, easy. But if points are far apart or obstructed, we use differential leveling, moving the instrument multiple times to sort of leapfrog across the site. Surveyors often use loop leveling, starting and finishing at the exact same known benchmark just to ensure those differential leaps didn't quietly accumulate any errors. If we just need to quickly transfer a benchmark over a long distance without needing insane precision, we'll do fly leveling. And if we hit a massive obstacle, like a rushing river, we use reciprocal leveling, taking observations from both banks to cleverly cancel out the physical distance gap. It's all about elegantly adapting to the environment. A highly specific application of these methods is something called profile leveling. Instead of just trying to find one single height, readings are taken continuously along a fixed center line. Engineers use these profile levels to plot longitudinal sections. Think of it like mapping out the exact ups and downs of the ground's surface. This is absolutely critical for fixing gradients and figuring out the massive earthworks required when you're designing roads and railways. But hey, What if you can't physically place a staff on a point? Let's say it's the top of a mountain peak or some towering antenna. That is where indirect methods come in, specifically trigonometric leveling. In this case, direct staff readings are entirely replaced by good old trigonometry. By simply measuring the horizontal distance from the instrument to the target and reading the vertical angle of elevation, we can mathematically calculate the height of completely inaccessible points. Pretty brilliant. Section 4. Calculating the reduced level. The verification math. Okay, so we've gathered all our readings from out in the field. Now, we have to meticulously process our data to figure out what those staff readings actually mean. And we are doing this in pursuit of one single holy grail number, the reduced level, or RL. The RL is simply the elevation of any specific point above or below our adopted datum. We calculate this by adding our first backsight reading to our known benchmark to find the height of our instrument. From there, we just subtract our forward foresight readings to find the new reduced levels of the ground points. Now, when you're calculating dozens of reduced levels by hand, mistakes are going to happen. We're only human. To protect against this, surveyors use this beautiful built-in safety net called the arithmetical check. It states that the sum of all backsights minus the sum of all foresights absolutely must perfectly equal the last reduced level minus the first reduced level. If these numbers balance out to a zero difference, it guarantees for sure that the manual mathematical reduction of your field data is completely flawless. Section 5. Eliminating leveling errors. The reality check. Flawless math is wonderful, but as we know, physical reality always likes to introduce some errors. What are the natural antagonists trying to ruin our perfect horizontal line? Well, first, the instrument itself might be misaligned. Then there's the Earth's curvature. Over really long distances, the planet physically drops away from our straight line of sight. We also face atmospheric refraction, where the air literally bends the light entering the telescope. And of course, there's always human error, like simply writing down the wrong number in the field book. So, to combat instrumental error and check if a level requires a permanent adjustment by a technician, surveyors use a highly practical, clever field trick called the two-peg test. You hammer two pegs into flat ground exactly 60 meters apart. You set up your level dead center at 30 meters and take a reading on both pegs. Because you're exactly in the middle, any internal calibration error completely cancels itself out, giving you the true level difference. Then you move your instrument just 3 meters away from peg A and reread both pegs to get the apparent difference. If that true difference and the apparent difference don't match up, your instrument's internal line of collimation is broken and requires a permanent fix. To put that into perspective, in a two-peg test, you might discover a discrepancy of just 24 millimeters. Now that might sound tiny, right? Almost negligible. But ask yourself, if an unchecked calibration error of just 24 millimeters can cause water to pool in the wrong spot on a local construction site, what happens when that exact same unchecked error is compounded over the design of a 100-kilometer irrigation canal? The consequences would be absolutely catastrophic. And that right there is why the meticulous, structured, mathematical art of leveling is the literal foundation of the built world around us. Thank you so much for joining me for this explainer.